Oh, was it?
I'll be back.
All right, we haven't practiced this at all, so we're gonna just kind of wing it.
Yes.
Oh, we went off. Oh,
Yay.
wait, that's the wrong
That's the other one.
Yeah, that's the other one.
Nice presentation. It's a nice presentation.
Don't lie to me.
I'm not lying. It's in the laundry. I didn't want to be stinky.
Does that need the accompanying paperless?
Why are you so red?
You didn't wear your own shirt.
He has a black shirt.
Oh, you don't have one? We've had like 3 events in a row.
why is it not doing full screen? That's presentation mode.
What? Looks like what?
All right,
That is an issue.
So, we all know that the GPS and the great outdoors are like a match made in heaven, right? But you add a rev control hub in there, isn't that more for like indoor robots? Well, it's certainly not built to withstand the weather. It's reliable for the indoor robots. It's not the greatest for the outdoors, but it's what we're given, so why not give it a shot?
Thank you. Right, so this presentation is about precise GPS navigation for outdoor mobile robots, which brings up a few questions like, where am I? Where do I want to be? How do I get there? And those problems are like solved by different GPS, I guess, components. Like, where am I? That problem gets solved by continuous localization of the robot. Where do I want to be? Gets solved by path planning. And how do I get from here to there? Gets solved by real-time navigation, which we're going to explain. And then there's also this bottom question here, which is like, how do I avoid things that get in the way? Which is kind of the biggest problem when it comes to outdoor navigation, and it's not something that's being solved by this system because it's just so complex.
So when you think about localization, think about how accurate you want to be. So there's some cases where you want sub-meter accuracy, like in a robot motor, you don't want to be in flowers. Geoscribing, when you're like drawing a football field or marking the lines on a parking lot, you don't want squiggly lines. And like sentry robots or sidewalk robots, you want to be on the sidewalk, not on the grass or in live traffic.
so, so you can see right now it says GNSS instead of GPS, and I'll address that shortly, but these are sort of the accuracy ranges depending on the kind of technology that you use. And you can basically look at a cost curve and say the cost is going up as we're going down and across this frame right here. So phones and tablets, most phones and tablets these days are also sort of in that same consumer area, so that's about the kind of accuracy you're getting, 3 to 5 meters of uncertainty. To get beyond that, to get into the sub-meter range, then you're talking about some more advanced techniques and higher end equipment. So, you know, the United States started with GPS and sort of offered that to the world. Now there's 4 major constellations and there's sub-constellations, so there's all sorts of satellites out there. But if you choose a receiver that can see the full 89 satellites of the entire system, then you've got that much better chance of getting enough satellites in view at any one point in time under your changing conditions. You've got trees in different locations and buildings and things like that. So anything you can do to maximize the number of satellites you can see at once is a good thing. And if anybody's jumping into, I don't know if anybody's jumping in on any of the slides, but feel free to. So how it works is you gotta have correction. To get into the sub-meter accuracy, you gotta have active correction going on. So in the industry, you'll hear the terms rover. We've got rovers over there, we've got base stations. Rovers, that's your moving location. That's the one that you really want to know really well. Your base station, and that's equivalent to the robots that we're talking about. The base station is fixed, it's not moving. You can get temporary base stations, but while they're in operation, they need to have a well-known location. And you can see that they're listening to the same satellite at the same time. They're actually listening to multiple satellites, but they're looking at the same satellites at the same time. They're both receiving those signals. The difference here is the base station knows where it is. So it knows what it should be receiving, right? And it can calculate the error as a result of that. And if it shares those error solutions back to the rover, then all of a sudden the rover has extra tools to really refine its location. And you can get into centimeter level accuracy using this. This is the receiver that we chose to use. This is the ZF9P from U-Blocks. It can see all of those constellations at once. It can do multi-band. So the traditional GPS was just L1 band. Now there's an L2 band, so you get two separate bands coming in from your antennas, two different frequencies. Again, it's a better chance of resolving those satellites, especially when you're up against buildings and things like that, so it just improves your reliability. Like I already said, 300 centimeter accuracy. This particular one has USB interfaces, it has two UARTs, it has I2C, it has SPI. You can find it on boards already mounted, so for in the around the $300 range, and some of those even have Bluetooth, right? So they connect the UART to a Bluetooth and you can get it out that way. The bottom one is that this can both generate and receive correction data. Can't do it both at the same time. It means that you can use it either as a rover or as a base station. So if you get two of them, price keeps going up, but you're no longer dependent on external systems if you set up your own base station. We chose not to do that. We chose to get our correction data from a free service called Rtk Go. This is a network of people who are running these GPS systems that publish their solutions freely. As a result, so it's completely free, but you're not like guaranteed a certain level of service. I will say that the Iron Rain Robo Dojo is sort of in the middle of the screen. That's where we practice. That's my house. Arlington 76017. That is a base station that we've been using at the location. So you saw, if you were at the Mechavator presentation earlier, that is what we were using for controlling that robot. VN1, I used to live closer up in that direction. I used VN1 for 2 years. It's been there, it's been rock solid. So nobody pays this guy to run this thing. He just offers it for free through the network, and it's been rock solid. Don't really know anything about the FLYSET. I know it's been there, but you know, and we are right now, we are right here, roughly. So getting back to what you actually get from an accuracy standpoint. So this is all using that same F9P receiver, right? I'm going to show you a series of slides with different levels of accuracy involved. This one is called Differential GPS. It's a little bit better than your normal. It was sort of like the I think it was the yellow circle on the thing before, but it can get down. So that white square right there that has the red square around it, that white square is basically like the size of an FTC field, right? So that's your reference. So it's a little bit fuzzy, but we're zoomed in on the sort of messy area of my previous backyard. And the green blob is taking 30 minutes worth of readings. So it's about 1,800 readings, and you see that it's getting sort of like any particular reading could be anywhere inside that blob, You can't predict where it is, right? So that's your uncertainty. This is got a little bit of correction through the WAAS that's published by the FAA. And basically it's associated with airports, so it actually helps guide jets in. But it's not, this is like older technology, this is not real-time kinematics. All right, so now what we've done is that was also using a single band antenna. So basically that $7 antenna you can get from just about anywhere. This one has been upgraded to an L1 and L2 antenna. And you can see that all of a sudden it's not as blobby, it's not as wide, it's a little bit more focused, and the readings from point to point drift a little bit. They don't like jump all over the place. But there's still a lot of inaccuracy. So now you can see that there's a 4-pixel square, right? Still 1,800 readings over 30 minutes. It's not moving. Now in all of these circumstances before, the antenna is just sitting there on a tripod. By the way, it's the antenna that matters, not the receiver's location. So the antenna is just completely stable, but this time we're using that VN1 base station correction data, and we send that into the receiver. The receiver then all of a sudden has the magic to compute its accurate location. That thing is rock solid, right? And it's still not in a great location. We're like, 6 feet from the eaves of the house. It's kind of hard to see there, but okay. And so this is the same thing, except I just pick up the antenna and I just walk around the yard with it. And so it's not super accurate. I'm walking around furniture and stuff like that. But you can see that it's tracking the path, and that's just 30 readings in half a minute. This is what you don't want to do. People always ask me, can you do GPS indoors? And sometimes you can get a GPS lock. It's actually very difficult to. It's better to go outside, get your lock, and then bring it inside. And guess what? You can hang on to those satellites for a while and you can keep getting readings, but the readings are a mess. So the red square there is the entire frame of view of those previous slides, right? So we're zoomed out here and you can see it's just swinging all over the place. So completely unreliable when you're indoors. Don't even try it. All right, so this is something's interesting. Okay. So this is the connection diagram for what's happening on the robot. So we're going to start up here. This is our antenna. This is a dual band antenna. It's got a magnetic mount in it, so you can. In our case, we threw it on the top of the excavator. It has a metal roof, and it just like sits there. But you can also bolt it down. You should have a ground plane under it. It's not shown here, but you need a disc about 6 inches in diameter that prevents backscatter from the ground. So it basically, if it sits on top of there, signals bouncing off the ground and coming back up, can't mess it up. It's connected over coax. This is our Rtk receiver. This is the one that's doing all of the magic, but it still needs to have those correction mechanisms. It is connected to the control hub via USB. The control hub is talking to a hotspot. So this is not the way we normally use control hubs in FTC, where it's acting as its own access point. It's getting the internet through a hotspot that's going through broadband to the internet. It's connecting to rtk.go.com saying it wants to know about a particular base station. Those messages get sent back and it comes all the way back in here. And then this one sends back the location to this, and then all of a sudden the robot knows where it is. This is the software view of this. So it's basically what I just told you. There's a standard Android hardware stack. There's a piece of software that's running on your control hub called FTC Access Point Service. And it's actually labeled Hotpot. It should be Hotspot, I'm pretty sure. But that is part of the, that's like a bug in their code or a typo in their code anyhow. This is the piece of software that makes it act like an access point so that your driver station can connect to the control hub. You have to kill that. There is a way to do it. We've got a separate video that we're going to publish about how to do all of this configuration, because it's not simple, it's not straightforward to get to this point. But you've got to disable that service in order to be able to turn on normal Android Wi-Fi. Because we need to connect from here to, well, this doesn't show it, but through the real hotspot, we need to be able to connect through it to get an internet connection. Obviously, that's completely forbidden in FTC. You're not allowed to connect your robots to the internet. But if you kill this, then all of a sudden you can turn on normal Wi-Fi. This is a piece of software that I wrote. It is a location provider. So this is an Android system service. And its job is to subscribe to those base station messages through here, forward them onto the ZF9P through USB, and get the corrections back, and then turn that into what's called basically a location system message. And so any apps that register themselves as interested in listening for location updates on Android will get that solution. So all of a sudden, any other apps that are listening will also get that really highly precise version. So we're using OpenRC as our robot controller, open source version of the FTC robot controller stuff. And so it is listening for those location updates. And this is the software that does the actual, carries out the implementation of the navigation that we've requested. Path planning, super simple. We just use Google Earth, right? So these are two different locations. So if you saw the Mechavator running previously, so I'll show you shortly what it's actually doing. But this down here, this little square right here, that's about a 16-foot square, something like that, maybe a little bit bigger. I forget the actual dimensions. So that's my house up there. This is a cleared area now. This is actually older imagery, but that's what I needed to do in order to get the trees out of the way. So it shows what the previous clearing was. And I basically just drew that as a polygon on there, export it as a KML file, and then I've got the series of coordinates that we need in order to generate our path. This is a different location. This is a softball field up in North Dallas. And this is just the team numbers thrown on top of it. And then we can basically export, we basically have to manually trace over that, but then we can export that again as a KML and as a path that the robot might travel. So we didn't take the excavator to a softball field. That was this robot, which we call Beachcomber. What's going on here? Oh, all right, and this is it. This is the excavator. So it's starting off in a calibration run. I've sped this up 5 times. You can see that it's shaking all over the place. That's really bad PID setup, right? So this is when it was sort of an earlier run. So all it was doing for calibration, it was just saying, go straight, look at the IMU, let's go straight for 15 seconds, and let's see what our first position was and what our final position was. And from that, we can get a bearing, right? And since we're accurate, we know it's a true bearing. And then we use that to correct our IMU's understanding of what the bearing is, right? So then we can follow the IMU. Here, it was going in real time, so you can see how slow this excavator goes. So it's not really a huge safety hazard. And in this sequence, we're basically going through that square path 10 times, right? To show how repeatable and how accurate it is. So we got this tiny little cones. You probably recognize those from last season, marking it out. And then here, if we slow it down again, to show that while it's still doing its navigation path, but the arm can be articulated at the same time. Okay. So this, let's try it this way. All right. Okay, so this is this robot. We call this robot Beachcomber. We had a light bar, an LED light bar on the back of it. This is taken from a drone about 100 feet up, looking straight down on that field at night. and we're just asking you to trace the team number through, and we're just using compositing to show it as a progressive buildup of the path. You'll see that as it gets a little bit further on, the path starts getting more and more jaggy. See how jaggy it's getting right there? That is not a fault of the software or the GPS solution or anything like that. It turned out that we had basically a wheel was binding up, and it was getting hot enough to get worse and worse, and so it was just having trouble correcting for it. But that is basically our example of what we call geoscribing. During the daytime or at the beach, we call it beachcomber because we've traced patterns in the sand at the beach when we have that rate established on the back of it. That's it. That's all we wanted to present. More to come. We hope to release a video of the actual excavator, more details on it. Any questions about the GPS stuff?
Wait, so how sped up is that video?
That one?
Yeah.
Boy, that was a while ago we rendered that. I would probably guess that was probably also 10 times sped
Okay.
up.
So,
Okay.
is it also using any other sensors to determine its location? Is it a combination of GPS and like encoders or something?
Nope, not using any encoders on this.
Basically, like where
The excavator is really hard to put encoders on. We were thinking about different ways of doing it. So you always want redundant, sensing and things like
I
that.
think because he's using differential GPS, which is accurate enough in centimeters.
You don't really need. Yeah, don't really need it.
Yeah, you don't need
In the environments that we're in, right? But you're right. You should always have backup sensors. But we didn't have any encoders on this. We didn't. There's no need for it. It's so accurate.
Is that free volunteer like base station service at all? Because I know how
Yeah, it is.
expensive that was. Because I was working with Verizon to use a commercial one.
Yeah.
They call it Bullseye. So they got grades of like base station, mirror stations.
Yeah.
And to use fractions of GPS data.
Yeah.
That's pretty expensive.
Oh yeah. I mean, when I first started looking at this kind of stuff, the equipment was like, $5,000 to $10,000, and these correction services were very, very pricey.
Yeah.
It's all coming down. There are there's another way. There's a sort of a newer breed of receivers that are triple band and can actually get subscribe to correction data again from satellites. So you don't need to have broadband. So you can do this way out in the boonies. But it's still it still costs more per month to get those kinds of services. But they're coming down. So, but yeah, this having a completely free network, and we're gonna put up a base station at our place too, so that places that are further down south will have a good correction signal as well.
So you don't need to pay any service fee for receive any of those signals?
That's correct. Not through our. Well, let me correct that. You still have to have an internet. You need to have some sort of internet connection, right? So that usually means like a broadband hotspot or something like that, and it doesn't work in areas where you don't have some sort of connection. But yeah, it's free. There are paid versions of that where what you're basically paying for is the assurance that those signals will always be there, right? There'll be more of them. It'll be a richer, denser network, and they'll have guaranteed uptime for them. So if you were doing like agriculture or construction or something like that, you probably want to not rely on what people are just putting up for free, right?
And that receiver will receive 4 types of satellite?
Yeah, it does 4
GPS,
constellations. So
Beidou and Galileo, right?
yeah, it does Beidou, Galileo, GPS, and GLONASS. So yeah, all of the 4 major ones.
I think there was a community like the hand radio,
Pardon?
like the hand or like the volunteer radio.
Oh, ham radio?
Yeah.
Yeah.
It's kind of like that idea, and
Yeah,
like
kind of.
that
Yeah.
community.
And again, you can roll your own base station. So then you have to figure out how you're going to get the information from your base station to your rover. In those cases, your base station is probably a lot closer, and you might be able to use line of sight radio like you use on drones, or there's a whole bunch of them these days. Yeah. It's not a high bandwidth, it's only, like 9600 baud would do the trick. Right, you don't have to have a huge flood of messages coming back from the correction source.
Yeah, I think it's amazing to put all the things together as a solution. I think
Yeah,
that's
it's
really
a total
great.
integration, yeah, it's like, yeah. All right,
Okay, I guess that's
we
it.
finally get to go home.
Wait, no, we have a drawing.
We
Wait,
have a
wait,
drawing.
wait, the
All
money.
right.
Um. Okay, only you guys are eligible. You guys. Yeah, screw you guys.
I mean, a bunch of random numbers in here.
No, just ask Siri, bro. Okay.
Alright. Wait, I'll think of a
You
number.
can, like, sit down so we can like have you guys in a line, and then just like pick the. Okay, just ask Siri. Yeah.
Here, I'll ask Siri. Wait.
Okay, we'll just have it like
You take 3.
1, 2, 3, 4, 5, 6, 7, 8.
8.
Yeah.
Alright.
Or like,
Alright.
can you sit there? I guess we're just gonna like use a random number. Okay, so there's 2 prizes, right?
1, 2, 3, 4,
Yes,
5,
there-
6, 7.
yeah.
Alright.
There's 2
Then
prizes.
we have $25 Soho City, and then we have $50 Harbor Freight. Whoever won, can you just come up to me and give me your email so we can forward that coupon code to you later after the workshop? And now I'm gonna ask Siri to pick a number from 1 to 8.
Okay.
Hey Siri, pick a number from 1 to 8. Wait, I don't have service in here.
Wait, what?
Yeah, Siri doesn't work without Wi-Fi. Pick a number from 1 to 8.
Okay, this, can you try like asking Google on your laptop?
Does Google answer the questions like that?
Oh, number 4, right one.
I hope so.
He's number 4.
Okay, so there's 2 of them, right? So
Yeah, 2 of them. Let's do the $25 Soho City gift.
just pick a number from 1 to 64.
64.
Yeah.
Why?
Because like, there's 8 times 8.
What do you want? You want a number from 1 to 64?
Yeah. Okay, you know, screw that. Okay, just do 1 to 8. Just do 1 to 8. That's too complicated. Okay, so let's see.
1, 2, 3, 4, 5, 6, 7, 8.
This is the reward for staying over by how many minutes?
By an hour.
An hour? Wait. Oh, wow. It's an hour.
It's referring me to a random number.
Oh my god.
Oh, come on. Oh, because I'm on the school
This
network.
school's really strict for some reason. Like, can't use GitHub.
I can switch to my hotspot.
Yeah, but the problem is I don't think anyone's hotspot.
My hotspot was working earlier. Don't see it now.
Wait, let me see if any of the other generators are.
Or just think of a number from 1 to 100, whoever's the closest gets it.
But then
Yeah.
family friend. Like,
Oh,
here we go.
That one to them.
First
then
one,
we
this is
got-
for the Servo City. Okay.
$25 Server City.
$25 Servo City.
Yeah.
Okay. Let's go. Number is
5.
5.
1, 2, 3, 4, 5.
Yeah.
Yeah.
Five
Alright.
Servo
Let me get your email.
Okay. And then what was the other one? The
$50 Harbor Freight.
what is, please explain.
It's a store, I think.
Okay.
This is
Alright.
more with hardware stuff.
Okay. 3, 2, 1.
6.
Six.
Your friend.
Man, needed that.
Alright. Alright, thank you so much for attending in. This is the end of the workshop. Thank you.
Okay, we can finally stop the recording. Bro, my phone's like.
Thank you so much.
You can't stop both of us.